Hello friends, in this video lecture we are going to discuss the dynamic response for single area load frequency control. So let us begin. So friends, in our last lecture we have discussed the steady state response of the load frequency control model. Now let us discuss the dynamic response for the load frequency controlling model. Okay, see here. Now I'm interested to find out how this block diagram will respond to change in load in dynamically. Okay. Now in order to get the dynamic response, it is better to have the system in time domain instead of having the system in Laplace domain. What we have done, we have modeled our system in the Laplace domain. See, Laplace domain is nothing but it deals with the frequency, and the time domain it is actually dealing with the time. Both are having some advantages and disadvantages. In time domain, the advantage is that we get to have the real values. Okay, whereas when we are dealing with the Laplace domain, certain mathematical operation becomes very simple. So that is why sometimes we go for Laplace domain and sometimes we go for the time domain. But here, in order to understand the dynamic response, we should get the system transfer function in time domain. Okay, that characteristic equation, if you remember, for the whole block diagram, we got that characteristic equation. If you remember that, of course, we have kept that speed changer setting to be 0. We got some value here. Okay, that kps upon some 1 plus something terms was there, okay, into that delta pd divided by s. This was the quadratic equation, or this was the characteristic equation we got for that block diagram representation. Here what we are going to do is, let us take the Laplace inverse of this characteristic equation. Okay, now when you are going to take the Laplace inverse of this characteristic equation, it is a third order equation. Okay, so again it becomes difficult to solve the third order equation in time domain. So the dynamic response, we can approximately calculate it for a particular case. Okay, or else what we can do is we can apply the first order linear approximation. The first order linear approximation. See what we are doing, the actual block diagram, if you remember, it was containing the blocks like this was the summer. Then we had that SG block, that is speed governor block. Then we have that turbine block, TT block. Then we have one more summer. Then we have that power system block, generator load model block. And then we have that uh, regulation of the speed governor. And this is how the actual block diagram we have for the alternator. Okay, this we have modeled earlier. Here of course we have that load, incremental load we are giving, and here the commanded output power we are changing. Okay, this we have discussed already. So you see here, with some by examining this blocks, okay, that is the speed governor block, turbine block, power system or generator load model block. Of course, these blocks are having transfer functions in terms of gain and in terms of time constants. So if we examine this and if we apply some approximation on these blocks, then we can reduce it. It is possible to reduce it. Okay, if we take a typical system, or if you take a typical values of these time constants, see this time constants comes in this order. The order of the time constant we get is the time constant of speed governor is less than the time constant of the turbine, and also it, and both of them are very less as compared to the time constant of the power system. If I take a typical values of these time constants, then it becomes typically this TSG is having value as 0.4 second. Of course, then TT, that is turbine time constant, it is having value as 0.5 second. Okay, actually the range of this TT is in this is the typical value, but this turbine time constant, it varies. Okay, it varies from the range zero point 0.2 second to 2.5 second. Okay, it depends on the type of the turbine. Okay, and of course that reheater storage time, these are the factors that govern the time constant of the turbine. Then the time constant of the power system TPS is 20 second. Typical values I'm taking. Now if you compare here this TSG, value of this TSG, this time, turbine time, it is very less as compared to the power system time constant. So what we can do over here is we can let this TSG is equal to TT is equal to 0, as it is very small as compared to the TPS. Of course, we have the gain control with us, particularly the gain control of the speed governor KSG. We can control it. Of course, we cannot control that KT. KT, it is a fixed. KPS also it is fixed. Of course, that KPS, it depends on the power system constant, that B value. But of course, that B value, if it is a constant value, so of course that KPS is fixed, KT is fixed. But we can adjust that KSG, and we know that we always adjust the KSG in such a way that the product of KSG, that is the gain of the speed governor and the gain of the turbine, should come approximately equal to 1. Okay, now if we apply these approximations, if we apply these linear approximations, then this block diagram, whatever block diagram we have here, we can reduce this block diagram to this block diagram. It is possible to reduce. You see, the gain KSG and KT, the product of these two we are making 1. The time constants TSG and TT we are making it 0. So we know that when the blocks are in series, they get multiplied. So if we apply this, or if we put these values, we get the resultant of these two blocks as 1. So now this block is it is a first order approximate block diagram. Okay. So now in this block diagram, let us see how the frequency will change for the small change or the linear increment in the power demand. Okay, we have to observe how the frequency will change. Okay, now looking at this block diagram, let us write those equations. Okay, with this block diagram we can write delta f of s. Okay, again let us keep that commanded power to be 0. Okay, so we get here, you just see what we can get here. What is the input? This is the output, del fs. This is my output and this is my input. So output by input we get. How we write? This block divided by 1 plus this block plus this block into gain. Okay, so I'll write here, you just observe. I'm writing that value here. It will be KPS divided by 1 plus STPS, we get, of course, divided by 1 plus KPS divided by 1 plus STPS into 1 by R, of course multiplied with that incremental change in the load. Okay, again, as we are going to consider the incremental change or step change in the load, we have to divide it with S, because the Laplace of the step signal is 1 upon S. Okay, again you see here that power demand in this block diagram representation PD, it is a negative signal. Okay, so we should write here that negative sign. Okay, so we'll put that negative sign here. Okay, let us solve this equation. Let us apply some mathematical operations to reduce this equation or to make it simple. PC of s is equal to 0. Now let us multiply and divide with 1 upon that 1 upon, okay, not 1 upon, let us multiply and divide with 1 plus s tp of s. 1 plus s tp of s. If we multiply this, what happens? These terms, this term will get cancelled. When it get multiplied here, it get cancelled here, but it will multiply with this one. So we will get here, definitely we will get here. The numerator will have minus kps divided by this bracket will get multiplied here. So we'll get here 1 plus s tp of s, okay, plus this term kps divided by r we will get. Kps divided by r we get, and on this side of course we have the delta pd of s upon s. Okay, now let me take tp of s as common from this denominator, or let us multiply and divide with 1 upon tp of s. Okay, 1 upon tp of s. So what will happen here? We get this equation as, it will be, see this, minus kp of s divided by tp of s we are getting here, divided by these terms. Okay, of course this is in bracket. So when we multiply this in bracket, what we get here is, here the first term will be 1 upon tp of s, 1 upon tp of s, then the tp of s get cancelled, we get 1 s here only, and here we get kps divided by r tp of s. Okay, of course we have that delta pd of s divided by s here. Okay, let us rearrange these terms in the denominator. So what we will get here, we should get minus kp of s divided by tp of s divided by, let me bring that s term here, s into s plus, okay, these two terms, one divided by tp of s plus kps divided by rtp of s. Okay, so if I add these two terms, you just see how I'm adding, cross multiply this. So here you will get rtp of s, and this cross multiply this, kps into tp of s we get, divided by the multiplication of these two. So we are getting here r into tp of s square we are getting, okay, into that delta pd of s we get. Okay, now you see here I can take tp of s as common. Okay, tp of s from this and tp of s from this, if I take common, so that tp of s and that square will get cancelled. Okay, so as it is getting cancelled, so we are getting that delta fs at speed changer setting fixed speed changer setting, we are getting it as minus kp of s divided by tps divided by s into s plus, see we get r plus kps here, r plus kps divided by r tps into delta pt of s. Okay, so this equation we are getting from the block diagram, first order linear approximated block diagram. Okay, now let us take the Laplace inverse of that, because as I said, we have to when we have to observe the changes in the frequency due to the change in the power demand, we should it will be easy when we do the analysis in the time domain. Okay, so let us take the Laplace inverse of this. So if I take the Laplace inverse, so I'll get here delta f of t now. Okay, this f of t indicates it is in time domain. Okay, just take the Laplace inverse of this, apply your mathematical logic knowledge. You should get Laplace inverse as this minus r kps r plus kps into this 1 minus epsilon exponential in raised to 1 divided by tps in the bracket r divided by r plus kps into delta pd. Okay, now as I said, we can observe the dynamic response only for a particular case. Okay, so let us consider a particular case. Let us have some values of these terms we are getting here, and let's see what will be the change in the frequency. Okay, let us assume some change in the power demand, and with that we will see how the frequency will change. Okay, so now taking a typical system rating. So here let R is equal to 3, that kps is nothing but 1 upon p, keep this as 100. Okay, tps we have already considered it to be 20 second. Okay, assume that change in power demand to be 0.01 per unit value. Okay, now when you put these values in this above equation, and if you solve this, just put these values, delta f of t would be, now this is minus, r is taking value 3 and this kps is taking value 100. So we'll get here 300 divided by r is taking 100 plus this r is taking 3 and kps is 100. So we'll get here 103. Okay, this is 1 minus exponential minus 1 by 20 in the bracket 3 divided by 103. Okay, and this is 0.01. See why I'm taking it in per unit value, because this kps in this b coefficient, that b constant, we calculate it on per unit value. Okay, if you remember that b, it is dou pd upon dou f with respect to pr. We calculate that b with this value. Pr is the kW rating of the alternator. So if we get this per unit value, so as it is in per unit, consider the load to be in per unit. Okay, and if you solve this, you just see, when you solve this, you should get the value as delta f of t is coming to be, of course here we have that minus sign, so it is minus 0.029, okay, into 1 minus exponential minus 1.717 t. Okay, now if you convert into the frequency, okay, particularly if you want to take the frequency, so here you will get the frequency as change in frequency to be 0.029 hertz. Okay, so this is the change in frequency. But this much change in the power demand, we are getting change in frequency as this. Okay, if you plot this, see it is exponential term we are omitting here. Okay, when we plot this frequency against this exponential term, that is time term, so we get a plot. Let me show that plot to you. Okay, so this is the dynamic response of a change in frequency for step change in the load. Okay, we are considering a step change in the load. Okay, you see here, for the step change in the load, how the frequency is going to change. It is in minus value, so you see this is a change in frequency into -2. Okay, and this is against the time. So as soon as we have given, or we have considered that there is a change in the load by some step value, okay, then the frequency behave this way. Okay, this is the actual response. you can see some disturbance here, but after some disturbance, now my frequency is now settled to this point. This is the value 0.029 hertz. That is the change in the frequency. Okay, this was the scheduled frequency. At this earlier it was operating. Okay, this is the scheduled frequency. Okay, that is change in frequency. Okay, earlier the change in frequency was 0. Now the change in frequency has become 0.029 hertz. Okay, see, the change in the frequency, we have some allowable range. We can have the frequency variation up to plus or minus 0.5%. It is allowable range. So as far as if this change in frequency, if it is within this range, then it is okay. System is stable. But if this change in frequency, if it goes beyond uh, this range, then your power system is in danger. You may experience the blackout in your power system. You may experience a number of problems in the power system. The synchronism problem you may experience. Again, as I said, the whole system may get collapsed. Because of that, there may be a complete blackout may be there. Again, see, if we keep the frequency as constant, we can use the synchronous clock at various location where we have the electrical network. If we are using that synchronous clock for the time calculation, then if the frequency is showing so much fluctuations, so much variation, then your synchronous clock will also not show you the correct time. So you may miss that privilege of having the synchronous clock to monitor the time as well. So these are the some consequences which uh, we may have when the changes in the frequency, if it goes beyond this limit. Of course, that is ideally we expect the change in frequency to be zero, but practically some variation will be there. Okay, even if you take the example of India, practically we sometimes we don't have the frequency following this range also. Okay, if you see, we have that we can monitor that frequency. Okay, because government of India, they have that portal. If you want, you can uh, check that. Just go to this website, POSOCO. Okay, Power System Operation Corporation Limited, India. This agency is actually, it is taking care of the national grid. Okay, there you will get various reports. Okay, if you want to see the report regarding the uh, frequency profile, then you can go to this website, their website, and you can see the frequency profile. Sometime it will show that the frequency variation is from 49 hertz up to 51 hertz. Okay, so as you can see, it is violating this limit, because in India it is possible, because still we are not having that controllers of that uh, quality. Okay, of course, when you don't expect the change in frequency to be some definite value, if you are looking to minimize this, okay, if you want to minimize the change in frequency, then of course you have the uh, provision to go with the controllers. Okay, if you want, you can use that proportional controller. Controllers can be used to make this change in frequency approximately zero, near to zero. Various controllers are there. A proportional controller is there. Then you may have that PI controller, that is proportional plus integral controller. Then you may use that PID controller. Okay, this way smart controller is there, stochastic controller is there, uh, adaptive controller is there. Okay, various controllers are there. So as far as if your requirement is concerned, you have to choose the controller. Okay, because these controllers, of course, they comes with some certain advantages and disadvantages. So when you are going for the selection of the controller, you have to study those controller, and as per your requirement, you can choose the controller, and you can fix that controller in your system. Then what this controller will do, the steady state error. See, actually the change in frequency, it is actually the steady state error. This value is nothing but the error. So these controllers are used to make the steady state error as zero. So this controller, what they will do, they will put make this change in frequency to zero for the change in the demand. Okay, so this is how dynamic response we get for a particular case only. Okay, so with this this single area control concept over here. Thank you very much.